In this video, we will discuss the designing, testing, and findings of the Concrete Design Lab. The goal of this experiment was to find which materials and which proportions led to the highest concrete flexural strength.
To start our testing, we first tested the workability of mixes with varying water-cement ratios. This was done by performing the mini slump test on each mix. This video shows the slump test for the high water-cement ratio mix. This video shows the slump test for the super plasticized mix. This video shows the slump test for the silica fume mix. The diameter was measured at the largest spread 10 seconds after the mix dispersed.
The hypothesis of this group was that the use of Portland cement, silica fume, and pea pebbles would produce a concrete mix with the highest possible flexural strength. The use of a small amount of superplasticizer would also help to increase the flexural strength and workability of the mixture. The addition of steel macrofibers would also help to increase the flexural strength. We conducted research on which ingredients led to the highest flexural strength, using both online resources and the findings of our mini slump test. Through this research, we found that up to 10% of the mix could be constituted of silica fume to increase the flexural strength of the concrete. We also found that approximately 2 pounds per meter cubed of steel fibers could be added to the mix to increase flexural strength. Cementitious material in the mix included Portland cement and silica fume. Non-cementitious material in the mix included steel macrofibers, concrete sand, pea pebbles, and water. The superplasticizer was added as an admixture and it was accounted for as part of our water amount.
The overview of our mix design included 38.95 pounds of Portland cement, which is 17.4% of the mix, 2.805 pounds of steel macrofibers, which is 1.25% of the mix, 0.8268 pounds of silica fume, which is 0.37% of the mix, 94.31 pounds of concrete sand, which is 42.07% of the mix, 0.728 pounds of superplasticizer, which is 0.35% of the mix, 67.24 pounds of pea pebbles, which is 29.99% of the mix, and 19.31 pounds of water, which is 8.61% of the mix.
First, we added the pea pebbles and then the fine aggregate, also known as concrete sand. Next, we mixed in the cement. After that, we added the steel macrofibers. We then mixed all of these together. The silica fume was then added to the mix. We added the superplasticizer to the water and then add the water into the mix in 3 portions, while mixing the concrete between each addition.
Why didn't we go with this smaller aggregate? I know, look how, but this is good though, I feel like.
Here's our group with our finished concrete mix.
Once our concrete mixture was complete, we conducted the slump test on the concrete. The slump of the concrete was tested and found to be 8.5 inches. Next, we conducted the pressure method air content test. The air content was found to be 2%. Then the concrete mix was poured into 3 cylinder molds and 1 rectangular mold for testing. The beam and 3 cylinders were demolded after approximately 24 hours. The concrete was then left in the hydration room to cure for approximately 2 weeks.
Doesn't matter if you go into it a little bit, but you don't need to. That's turning the wrong way. Hold the cylinder with your other hand. With your right hand. Yeah.
Here is the testing portion of our project. First, the compressive strength test was performed on each of the 3 cylinders. Here is the compressive strength test of the first cylinder. Here is the compressive strength test of the second cylinder. Here is the compressive strength test of the third cylinder.
62. I think the other one would be. Oh, maybe not.
The average compressive strength found from the 3 tests was 4,872.38 psi. Next, the flexural strength was performed on the concrete beam. This video shows the beam being subject to a vertical load at 2 equidistant points along its span.
Where'd it break?
Here.
Well, awesome sauce.
The modulus of rupture of the concrete beam was 122.52 psi. Our mix design had the lowest flexural strength of the class, with a modulus of rupture of 122.52 psi. Group 3 had the highest modulus of rupture of 798.06 psi. Our rather low values could also be partly due to the fact that our beam was slightly dropped when being placed on the flexural strength testing machine, potentially causing an internal rupture before the beam was tested. Other groups did have different compositions as part of their mixture. While their exact values are not known, it was observed that the water to cement ratio varied between the different groups substantially, with some groups adding less water than us. This may have played a role in the strength of each group's concrete. As a group, we learned a lot from this experiment. The amount of silica fume and steel macrofibers should be increased next time to increase flexural strength. Another way to improve the mixture is to add more superplasticizer. A higher amount of superplasticizer would allow for the same workability while lowering the water content. The lower water content would then make the concrete stronger. We also learned that the flexural strength of concrete is significantly lower than its compressive strength. For this reason, steel rebar is commonly used to give concrete flexural strength.